Hi, I'm Brandon Gracey. I'm a high school math teacher. We are going to solve linear systems by elimination. I've already got a couple of videos on how to do this by substitution. Elimination is a little bit of a different situation. The key idea here is that you will have a couple of equations, usually in standard form, something like this, and another one maybe like this, and you might label them. So the key idea is that the equations are in standard form. There is no variable that is isolated, and you, instead of isolating a variable and using the substitution method, you can rewrite these as other equivalent equations, and then you'll be able to add them together to eliminate a variable. In the substitution method, you eliminate a variable by isolating it and then using another expression for it. Let me just flip back for a quick second. In the previous videos that I did, here we have y1 isolated, and we end up, instead of using y1, we end up using these other expressions for y1 in its place. In this particular example here, wouldn't be too hard to isolate y right there. You could do that, but we're going to go ahead and use the elimination method instead. The way we do it is by trying to change one or both equations so that they have, for one of the variables, they end up with the same coefficients with opposite signs, so we can add them together. But the very beginning looks exactly the same. If x1, y1 is an intersection point, then we know this to be true. We know that the first equation will be true at that point, and the second equation is also true at that point. And notice I'm writing them one on top of the other because, oops, sorry, that's a 10, or an 11 rather. I'm writing them one on top of the other because we are going to be doing a vertical addition in a minute. So there's equation A and equation B. Now what I'm going to do at this point is notice that I have a coefficient of 2 here and a coefficient of 4 here. If I were to double this equation, double everything, every term, including this other term, which isn't going to change, if I were to multiply through by 2, then this coefficient and this coefficient would match. They would be the same. And if even better, if I multiply everything by -2, they'll be the same but with different signs. So I'm going to do that. I'm going to multiply every term in the first equation by -2. I'll have -4x1, and then I'll have positive 6y1, -10. And that equals 0 times -2 is 0. And the second equation, b here, I'm going to leave as is. I'm not going to change it. Now again, I can do this because the top equation, these two here, are equivalent to one another. When you multiply through using a standard operation like multiply everything by 2, or add 2 to both sides, or divide everything by 5, that doesn't change the truthiness of the equation. It's still true for the same values of x1 and y1. So I have two equations that mean the same things as my original two equations. They're true at the same times. And now I'm going to add them together. When I do, see how we carefully crafted this? -4x1 and a positive 4x1. When I add those together, I'm going to get 0x1. You don't have to write this, but I am for now. I'm going to add these two together and get 7y1, and these two I'll get -21. That equals 0. So just looking at this little equation that I have now, 7y1 minus 21 equals 0. Well, that's pretty nice. 7y1 equals 21. Dividing both sides by 7, I find that y1 must be equal to 3. So that's nice. And now I know that if there's an intersection point, it happens when y1 equals 3. And so now I just need to find out what x1 must be. Unfortunately, compared to the substitution method, this is not as nice. I have to go back to one of my original equations, is the best bet, substitute y1 in, and then solve for x1. So I'm still going to have to do that isolation step in the end. So I'll just use A here, the first one. 2x1 minus 3 times y1, which is 3, plus 5 equals 0. 2x1 minus 9 plus 5 equals 0, or 2x1 minus 4 equals 0. 2x1 equals 4. That means x1 equals 2. So altogether then we have that 2, 3 is an intersection point. Okay, well, one of the nice things about this method is that it avoids fractions down until this sort of last part of the y1 and the x1. You don't have to have any fractions in here at all. It's all whole numbers, which some people are more comfortable with. So let's look at another example that is slightly harder. Here are equations A and B. Okay, so if we have an intersection point, then we know the two equations are both true at those points. Now, I can't, for example, double this equation, A, to get something the same as B. If I double 3, I'll get 6. That's not 4. If I double 5, I'll get 10. And so I can't double anything here. And similarly, I can't double anything there. In fact, there's nothing I can multiply one equation by, no whole number that I can multiply one equation by to get the same coefficients as in the other. But if I look here, these two, 3 and 4 have a least common multiple of 12. So if I multiply the top equation by 4 and the bottom equation by 3, then I'll have 12 for both of these. I could do the same thing here. Least common multiple is 15. I can multiply the top by 3 to get 15 and the bottom by 5 to get 15. I'm going to choose to do this by multiplying by 3 and 4, or 4 and 3. I'll multiply the top one by 4, and I'm going to multiply the bottom one by negative 3. I'm choosing to multiply by negative 3 so the signs will be opposite afterwards. Okay, so the top one will become 12x1 plus 5 times 4 is 20y1, and minus 28 equals 0. 0 times 4 is 0. On the bottom, multiplying by negative 3, watch that negative 12x1. That's going to be negative 3 times negative 3 is negative 9. And then, once again here, negative 9. So these two equations are equivalent to these two equations. They've just been multiplied through by this factor. And so now I'm going to add them together. Now, if you didn't multiply by negative 3, and you ended up with 12 plus 9 and plus 9, you could subtract the equations. But people tend to have a little bit harder time subtracting integers than they do adding integers. So that's why I'm recommending that you always try to end up with two coefficients that are the same but with opposite signs. So here I end up with 0x1. Here 20 minus 9 in this case, because it's plus negative 9, will be plus 11 y1. And then over here, that's going to be negative, what's that, 37 equals 0. Okay, I think I got that right. Okay, and now let's do 11y1 equals 37, and y1 equals 37 elevenths. Wow, that's pretty gross. That's not the kind of thing that you're going to be able to graph and find the value of, right? All right, so now, once again, we have to substitute this value for y1 back into an original equation to find out what must x1 be. Give myself a little room here. I'm going to choose, let's see, 11s. That's not a nice thing at all. So 3x1 plus 5 times y1, 37 over 11, minus 7 equals 0. Okay, so I just chose to substitute back into my original A. I'm not substituting into this one here for two reasons. One is these numbers are a lot bigger. And also maybe I made a mistake along the way. I might catch it here. All right, 3x1 plus, let's see, 5 times 37. Well, 5 times 30 is 150, and another 35 is 185 over 11, minus, writing 7 as a number of 11ths is 77. 3x1 plus, how many 11ths do I have here? 85 minus 77 would be 108, I think. Think about that for a second. Yeah, I'm pretty sure. So 3x1 equals negative 108 over 11. Now, is 108 divisible by 3? It is, so I'm going to divide both sides by 3. I'm going to get negative 36 over 11 for x. Oh, sorry, I'm off the screen there. Okay, so that means the intersection point is, the x part is negative 36 11ths, and the y part is 37 11ths. Okay, not very nice numbers, but that's how it works out. You can see we worked with all whole numbers right down till we had a one coordinate. And then the other coordinate, hey, it's going to be a fraction. That's how this works out. Okay, so I'm going to end this video here, and in the second part of elimination, I'll show you what happens when two lines are parallel and either distinct or identical.